Interrupts play a critical role in most microcontrollers, as they can quickly and efficiently respond to events. These might be things like button pushes, new sensor readings, or even internal timers. Zephyr's ability to abstract away hardware details means we can create cross-platform interrupt handlers. Let's see how that works. Previously, we looked at running multiple threads and thread synchronization techniques. Now, we'll start moving into various features and applications, as we'll start by creating a few interrupt-based demos. These include software timers, hardware counters, and pin change interrupts. We'll start with timers, and these are software-based timers that are based on the Zephyr kernel's system clock. You don't need to enable any hardware interrupts or counters to use the timers, but know that in most cases, because the system clock is based on an internal timer that's been set up by the vendor, it is still using interrupts. It's just abstracted away from us. The default resolution for the ESP32S3 is 100 microseconds. This is the best precision you're going to be able to get, but you can change this in kconfig. Note that this is less precise than using hardware counters, which we'll show in a minute, but it does have an easy-to-use, high-level API to set up and use the timers. Let's create our demo, and there's no need to create an overlay file for this, so it will be pretty straightforward. We'll create our demo timer. In here, let's create our source file. In that, we're going to create main.c. We'll include our standard input-output as well as our kernel.h from Zephyr. These are the two common includes we use for just about every Zephyr project. We'll first define our timer wait period. In this case, it's going to be 1,000 milliseconds. We're just going to put that in a pound define, and then we're going to create our ktimer struct for holding that timer information. Timers work on callbacks. So you set up a timer, you pass it in a function pointer, and it will call that callback function whenever the timer is up. The interface for this is defined by Zephyr, and it says that we need to accept as a parameter the timer struct that we've configured so that we can check it, reset it, do whatever we need. It's generally a good idea, especially if you have multiple things calling that callback, to check to make sure that the correct object is calling it. You can also use this to have different things happen depending on if you have different timers going off, even though you're using the same callback. So in this case, we're just going to make sure that the timer that triggered us is the timer that we configured. And this should demonstrate if you have multiple timers, you could have multiple things occurring. You could do a bunch of if statements based on those timers. First, in our main function, we're going to initialize the timer. We're going to call this ktimerInit function. We're going to pass in that timer struct we set up, as well as the timer callback function we configured. If we go to our API reference, we can look for that ktimerInterrupt function, and you can learn about it here. You can see that the callback that we passed it is invoked each time the timer expires, and we can also have another function that's called if the timer stops while running. We're not going to use that, but know that it is available, so we're just going to pass null to that parameter. Next, we're going to start the timer. We've initialized it, then we start it. We pass it in the initialized struct, the address of that struct, which is my timer that we configured earlier. Then we're going to define the duration, how long to wait before the callback is called once, and that is the second parameter. We're going to use this timer macro to set that up. We're going to say kmsec, and we're going to pass in the pound define of 1,000 milliseconds, and then we're going to set up a period. So you have two potential options here. The third parameter is the period. That tells Zephyr to call that callback continuously with a wait period of, in this case, 1,000 milliseconds. So you could have this function called once, or you could set it up to be periodic like we've done here. Then we're going to have our super loop do nothing in our main thread. We're going to use ksleep. Note that we're not using kmsleep, so we're not passing in a number. In this case, we're passing in this macro value that tells the thread to sleep forever. And like any good Zephyr program, we should return 0, even if we never get there. Let's save this. We need to create a couple of more files here, and that should actually be in our demo outside of the source folder. We're going to set up our normal CMake lists where we're going to define the minimum version, find the Zephyr package that enables all of those extra CMake extensions, Name our project, we'll call it demo timer, it's pretty arbitrary, and tell Zephyr where to find our source code. In this case, it's just source main.c, and add that to the app target. Let's save that. And we also need a prj.conf, and we're not going to put anything in it. This is a very simple demo. Let's go ahead and build this. So we'll go to terminal, new terminal. Workspace is fine. And we'll go into our apps and demo timer. We will build the application. Note that we don't need to define extra configuration or overlay files. And I did this incorrectly. Let's do always and -b for the board. That should build. Wait a moment. With that done, let's take a moment. We will refresh these. We'll go into the build folder. Let's go to Zephyr. Let's take a look at this .config file. And let's search for sys clock ticks per second. This tells you how many ticks per second occur in the operating system. In tick-based RTOSs, whenever one of these ticks happens, an interrupt would be thrown. The scheduler would run, which is usually a background task, in order to figure out which thread needs to run next. Zephyr, by default, is a tickless RTOS. That's why 10 kilohertz here seems a little high, whereas I'm used to like 100 hertz in tick-based RTOSs like FreeRTOS. In a tickless kernel like this, it means the kernel figures out the next task, sets an interrupt for that time, and then sleeps. So the kernel, for example, figures out that a high priority thread is going to need to run in, I don't know, 150 milliseconds. It sets a timer to wake itself up for that rather than waking up at every single tick. It's a little more complex, but it allows for better power management since the scheduler doesn't need to wake up on a regular basis. Now let's flash this to our board and we can see our really simple demo. Go into the repository where we've been working. Don't forget to activate your virtual environment. We'll use Espressif's ESP tool. That's a Python tool that will flash this program for us. We'll set it to our appropriate communications port. We'll set the chip to auto, baud to 92100. We'll reset before and after, write the flash, and write it to address 0. And we will pick our zephyr.bin from the folder we've been working in. Let's let that flash for just a moment. We'll open up a serial terminal connected to our COM port, and every second you should see timer flashing to the screen, which means that callback is being called every second. So we correctly set up a periodic timer to go off and call a callback function. As you can see, it's actually pretty straightforward. It's not a lot of code to set this up. These software-based timers are incredibly useful and very simple to use. You're not trying to configure any sort of hardware-based interrupts to make this happen. So if you need simple software timers and you don't need higher resolution, in this case more than like 100 microseconds, then these are really good to use. In fact, I recommend using these and only using the hardware-based ones, which I'll show you in a moment, if you need higher resolution, because we have to do a lot more configuration with things like the Devicetree to make that happen. Now, if you want to use a hardware-based timer, we have to do a little bit of configuration and know a little bit about the hardware that we're going to use, since every hardware is a little bit different. Note that Zephyr calls them counters. So timers is what Zephyr calls those software-based timers that we just demonstrated. But if you want to use a hardware-based timer, sometimes you see them referred to as timers when you're looking at hardware or you're looking at datasheets for microcontrollers. Sometimes you see them as counters as well, but Zephyr refers to them as counters. Just keep that in mind. Counter hardware, timer software. They are more precise because we are going to be relying on the hardware to set up and configure the timers to go off for us. However, they are trickier to use because we have to set up the Devicetree to use the underlying hardware, and our application code needs to be abstracted away so that it's still portable among different devices. We'll use this API to set up a counter for us, and it's going to call interrupt service routines, and those will be in callback form like we've seen before, but it will be in the interrupt service routine context. The vendor, in this case Espressif, should provide the underlying driver code for the low-level configuration so that when we call these functions, that code is called for us. But we do need to configure it in the Devicetree. To do that, we have to dig a little bit into the hardware to understand how to set it up because every vendor's a little bit different. In our case, let's go to section 9, and we're going to go into this interrupt matrix. And this is where we start understanding a little bit about how interrupts are configured specifically for the ESP32. You can see here the ESP32 S3 has 99 peripheral interrupt sources. We can connect them to physical hardware, like GPUs, or we can connect them to things like timers. These 99 interrupt sources are physically connected to the hardware. They might come from something like a pin, a UART, or another peripheral, or a timer, and it goes into a matrix, and you can map them to interrupts that occur in the different CPUs. These hardware sources that are physically connected in hardware, Zephyr calls these interrupt lines. So keep that terminology in mind when we start working with Zephyr. We need to configure the matrix to map these lines to different interrupts in each of the cores. There's 32 per core, 26 of which are user configurable, which you can see here, and 6 are reserved for internal or critical use, things like the watchdog timer, system ticks for an RTOS, exceptions, and so forth, so you don't want to touch those. So in reality, we have 26 per core that we can mess with. Zephyr calls these mappings interrupt numbers. So once again, we have interrupt lines, which is the hardware, and interrupt numbers, which can be assigned kind of arbitrarily by the user. These are numbers, these are software numbers that we can use to figure out which interrupt occurred and then call the correct interrupt service routine. Some microcontrollers, like this ESP32 we're looking at, allows us to map interrupt lines to the numbers, but note that some simpler ones, some maybe older 32-bit ARM Cortex M0 chips, might be physically connected and we can't map. So your lines are the same as your numbers. If we go to 9.3, you see the interrupt source table. This tells us which hardware uses which source. In this case, there's a number here. That is not an interrupt number according to Zephyr. This is an interrupt line. So we have our 99 lines, 0 through 98. We have the potential source. So this is hard-coded in hardware, or instead of hard-coded, it's probably an actual physically connected line in the microcontroller. And this tells us which registers used to configure it. The vendor's driver code for Zephyr should worry about setting up these registers, so we don't need to do that. We just need to worry about the source, the line number, and how to map it if we need to. For example, we care about timers. ESP didn't really name this very well. TG is timer group, and this is timer group 0, as opposed to timer group 1, which is over here. There are 4 timers total. There's timer group 0, timer 0, and then timer 1 in that group, and then there's timer 0 and 1 in timer group 1. So these are our 4 timers, ignoring the watchdog timer here because that's set up and configured for us. We won't be playing with that in this series. So if we go to 9.4, which is down here, we can see this register map. And this is just for our own information, but most of this should be set up for us. This is the offset address. We need to go back to, I think it was table 4.3 that we were looking at. This tells us the base addresses for the peripherals in the ESP32. And we scroll through here, we can find that 600C2000 is the base address for our interrupt matrix. So keep that in mind. We will see that when we start looking at Devicetree information. Finally, let's go to 12. This is our timer groups. As you can see, each group has its own watchdog timer, which we're not playing with, and we have user configurable timers, 2 in each group. If you're not familiar, watchdog timers reset the processor if they're not periodically updated, which is known as feeding the watchdog timer. This helps it recover from a freeze or a hang. If you've messed with the ESP32 for some time, you've probably run across watchdog timer problems. For example, when like a thread hangs while you're waiting for like a network thing to initialize, you'll see that the watchdog timer went off and reset that processor. It usually results in a fatal crash of the whole system. You can adjust these if you wish, but we're just going to leave them at their defaults for this series. Here's a diagram of how the timers are set up. We do have a 16-bit prescaler. This has the effect of dividing our input clock signal, in this case it's the APB clock, so that it counts more slowly. The counters themselves are 54 bits. That's a lot of numbers to store in these counters. If you're working with less powerful microcontrollers, these might be 16 bits or 32 bits, so keep that in mind if you're trying to write really portable code. You won't have 54 bits in most platforms. Now, let's look at the interrupt priority levels for the ESP32. I've gone to their ESP IDF guide to find these, because we're going to need to set a priority level for this hardware interrupt, which is different than the software thread priority or software interrupts that we examined earlier. Unlike thread priorities, higher numbers mean higher priority. 1 to 3 are general purpose use. This is usually where Espressif wants us to create our user level interrupts. You can set higher ones. 4 and higher, Espressif forces you to write assembly code so that your interrupt service routines are super fast and efficient. They're not even showing it on here, but 7 is a special non-maskable, that's NMI, non-maskable interrupt. This is reserved for things like the watchdog timer, power failure, critical faults, and so on. Usually we don't mess with these unless you're really getting into the nitty-gritty of the microcontroller. With that in mind, let's go look at how Zephyr sets this up. Let's close down this terminal. We don't need it right now. We're going to dive into the Zephyr source code because that seems to have a lot of information for us on how a lot of this works. We're going to go into DTS. We're going to go into the architecture Devicetree source. Let's go to Espressif, our ESP32S3, and the common DTSI, this Devicetree source include file, has a lot of information about how the SoC is set up. This is probably one of the most useful ones if you want to find things like, oh, how are the timers set up, or how is UART set up. This common, this SoC.DTSI is very useful because a lot of times you just need to look at this. Hey, how are the pins configured? And you just need to come in, find the label for this, and set status to OK in your Devicetree overlay file. Because the naming is a little bit different, the reason I looked up that address for the interrupt controller is because it's usually pretty easy to find here. If I'm doing this right, there we go. So just searching for that address gets us to the register property. There's the base address that we need, and there's the size and memory of the interrupt controller. So here's our interrupt controller. It's called int.c, so that's useful to know. It adheres to this bindings file, which connects it to the driver code that Espressif has written for us. And it looks like the status is already set to OK, so this should be enabled for us. Let's take a look at this file. By convention, Zephyr names the file the name of the compatible string .yaml. So we can just search for that, and we can pull it up right here. This has a reg property. This should map to the interrupt controller address, and subnodes are the individual interrupts, and each of those subnodes should have these 3 properties. So to declare an interrupt, we need to create an array with 3 cells, and those 3 cells should align with IRQ, which is the interrupt request or the line number, the priority, in our case this is going to be 1 through 7 that we saw in the documentation, and any flags to configure how that interrupt works. Back in our common.dtsi, let's look for timer 0. Here we go. So there's 4 timers, as we saw earlier. They are part of different groups. So you see we have that TG0, T0, that's the timer group. There's the other timer in that group, and then we have timer group 1. These map to different starting addresses based on where those configuration registers are. And they adhere to this Espressif ESP32 timer bindings file. This is the interface. And we can go ahead and search for that. So we'll search for YAML there. Here's the interface for the timer that we need to set up. Notice that there are a number of properties here. We need to define the group and the index. So group 0 or 1, and within that group, timer 0 or 1. We also need to define the prescaler. This is that 16-bit value that we saw earlier that divides the clock. As you can see, these are things unique to dealing with the ESP32. If we set up the Devicetree correctly, we can create portable code that should ideally run on different hardware architectures as long as we set up those Devicetree, usually overlay files, correctly. So back in the common, we see that it sets up the group number, the index number. So this is timer group 0, timer 1. It uses that compatible we just looked at, the memory location, and this is where it actually connects the timer to the interrupt. So if we find this, and it looks like IntelliSense is not finding it for us, we can try searching in Zephyr, find in folder, see where it's defined. So that's the C3, that's the S3. Here are all the interrupts that are defined for us that we saw in that documentation in the datasheet. So timer 0 should be line 50. Timer 1 should be 51, and that's in timer group 0. So let's go look for that. There's our datasheet. I believe it was section 9. So if we scroll down to 50, and there it is. Timer group 0, timer 0, and timer 1. That's 50 and 51. Sure enough, that lines up here. This is that entire chart in code form. That is how we're assigning that line number that is hardware to our actual interrupt, in this case, the timer. Let's go back to where we were looking at those. That's where those values are coming from. If we look at the interrupt controller, you can see that that array is defined by this interface here. So we have the IRQ, that's the interrupt line number. We have the priority. In our case, it's set to the default priority, whatever that's configured as. And then we have any flags. In this case, no flags. We're not passing anything in. We also have the parent. In this case, it's the interrupt controller node that we looked at earlier. So we can go ahead and find that again if you want to. If we search through here, there it is. This is the interrupt controller that was configured for us. And then you can see how various interrupts attach to it by using that interrupt parent and then passing in the label int C, which aligns to that label. Let's go back to our timer 0. Notice that while the interrupt controller is enabled, the timers are all disabled by default. So we need to use those. Looks like timer 3 is actually probably controlled by something else. So we may not want to use timer 3 in our applications since its status is not enabled here. I have not dug into what's using timer 3, but it looks like because these are disabled by default, that indicates to me that we probably are allowed to use these as a user or developer. So let's go ahead and use timer 0, and we will need to set status to OK to enable that. You also see that the prescaler is not defined here, even though the index and group are defined here. The prescaler, it's not required, so it's not defined. It defaults to 2, but we can configure that to something else when we go and modify this timer 0 in our overlay file. Let's take a moment, go back to this header file that we were looking at earlier. There's something interesting at the bottom here. So this is all of the interrupt lines, but if you scroll down to the bottom, remember where we saw IRQ default priority in that device tree? This is set to 0. There was no 0 level, so this is a little odd. If you dig into the driver code for this, you will find that 0 basically lets the controller assign a 1 to 3 priority level. So you can search for this priority. It's something Espressive has set up. You can find it defined in some of these ESP32 files. You see it basically just says, oh, use 1 or 2 or 3, and it's a low or medium priority. This is a little confusing. I haven't dug much into this, but it basically just says, oh, set the priority as whatever you want. You can set a different priority by overriding this priority level if you want to. If you want to have your timer be a high or lower priority, you can manually set it to like 1, 2, or 3 here. You would just need to, in your overlay file, when you're configuring your timer and setting status to OK, and defining that prescaler, which we're going to do in a moment, you could just set interrupts and redefine that to whatever priority level you want. I'm going to leave it. Default seems to be fine for what's going on here. Note that the priority levels are defined by bit flags, so I recommend using the macros here. These are generally the user level ones that we saw earlier in the ESP32 documentation. With that in mind, let's go ahead and create our counter demo. The counter interface is a little bit different than the timer that we've been using. In many cases, you could set a top that tells the timer to count up to a certain level, call your callback, and reset. In my experience, the ESP32S3 does not seem to allow a custom top value that is set in hardware or in software, and we can't change it. Not sure if this is a bug or just how the hardware is configured in the ESP32. So what this means we have to do is we can create this alarm callback, which says whenever the counter reaches a certain value, the callback is called, but that counter keeps going beyond that value up to whatever the max of 54 bits is. But what we can do in that callback is reset the counter every time it's called, which has the same effect as setting a top. It's just a few more lines of code. In our code, let's close down the files we've been looking at. We're going to create a new demo. Come up here. Let's close everything out, make it clean. In our workspace under apps, let's create a new folder. We're going to call this 09 demo counter. And I'm going to put interrupt here to let you know that this is occurring within the interrupt context, which is different than the main thread context. Let's create our boards. We're going to make our overlay here. And in that, we're going to create a new file, and we're going to call it ESP32S3 devkitc.overlay, like we've been doing. I like making aliases because it allows me to refer to something by a common name in code. We're going to set the myTimer alias to the timer 0. Timer 0 was defined in that ESP32 overlay file for us, and we just need to modify it here. And I closed it down on accident. But if we go to DTS, Extensa, Espressive, ESP32S3 here, it's the common. We'll leave this open so we can come back to this timer. So we're just going to be modifying this, and the overlay file takes priority. So the group and index are still going to be defined for us. This interrupts property will still be defined for us. We just need to set it to OK and set the prescaler, and we've enabled this timer. So that overrides that status to enable the device. And I'm going to arbitrarily pick some prescaler here, like 4,000. Just remember that in your calculation, you need to divide the APB clock by this amount to get your actual counter time period. Let's save that. Make sure I've got semicolons on everything because that's what Devicetree likes. Let's make our SRC folder. Why do you do this, VS Code? No, I want this in here. New folder, SRC. Yes, that's what I want. New file, main.c. Cool. Let's start by including the two usual includes, standard input output and the Zephyr kernel. And to use the counter interface, we have to include Zephyr drivers counter.h. Let's have our interrupt service routine execute once every second, which is 1,000,000 microseconds. Because we're operating at such a high level of precision, Zephyr usually wants you to use things in microseconds when working with these counters. It also has us set channel IDs for the various alarms that go off that we need to set when we configure the counter. I'm going to make a note here that this callback is occurring in the ISR context. If you're familiar with microcontrollers, this means that the main thread of execution has stopped. Execution is passed over to a different context, in this case, the interrupt service routines. Normally you want these to be as short as possible. If you need to do any extra processing, your best bet is to do something like set a flag so that your main thread or another thread processes the information that you need. Things like printing out to the console. So it's usually a bad idea to print to the console, but we're going to do that here anyway, just as a demonstration. Zephyr has a predefined interface for counter ISRs. It wants us to have these 4 parameters: the device that called it, the channel ID, which we have to pass in, that's why we set up a channel ID earlier, number of ticks, and some arbitrary user data that can be passed in. If we go back to our API reference, you can see that callback declared here. So we have a pointer, we have dev, channel ID, ticks, and user data. We must set up our callback like this with this signature when we are working with counters. So keep that in mind, which is why I have these seemingly arbitrary parameters here. It's actually declared in Zephyr for us, and we have to have those. As we will see in the main thread when we go to set it up, we create this counter alarm config struct. We're going to pass that into this callback as our arbitrary user data. Because we get in a pointer to that arbitrary user data, so we have to cast it back to that struct. In this case, we're just going to declare a new struct of that counter alarm config type and set a pointer to wherever that user data points to. We need that alarm config because that allows us to control the actual timer. This is where we want to reset that timer and put in that counter value. Zephyr handles this for us with this counter US 2 ticks, or microseconds 2 ticks. This sets the number of ticks that counter is going to count to. You can think of this as the counter counting down from this amount that we've set here. The vendor driver code handles configuring the counter for us. But in this case, we are configuring an alarm, since we are setting up a counter alarm config, to the number of ticks that it needs to count to, or down from, if you want to think about it that way. There's this handy counter microseconds to ticks. This takes the delay in microseconds that we have, in this case 1,000,000 or 1 second, we pass it in the device struct that we've configured in the device tree. This looks at things like the prescaler value and automatically figures out how many ticks of the counter it needs to count to reach our delay in microseconds. So we don't have to do that math manually, and this allows for more portable code if we set the prescaler in our overlay or device tree. Now we're going to set the actual alarm. Once again, we pass it the device, the channel ID, which is 0, and our alarm configuration that we just set up, and reset that counter to the number of ticks to give us 1 second. If we look at the documentation here, go find our functions. Go to our functions, let's search, counter set channel alarm, set a single shot alarm on the channel. We give it the device, which controls the actual counter on the hardware side using the vendor provided device drivers, the channel ID, which is just going to be 0 for us in this case, and this alarm config that we set up with a number of ticks, and this sets up the alarm for us. Note that we don't actually configure whether the counter is counting up or down. Everything's handled on the back end for us by that vendor code. If we go look at this, you can see how this is done. It's a single shot alarm, which is why we have to reset it every time we come through. We're not actually setting the top of the counter. We just reset this alarm. The thing we don't need to do is actually start the timer, because the timer can continue to run even though we've reset it. So as soon as we set the number of ticks and call this, so it only takes a couple of extra lines of code, when we call this, it goes ahead and sets the alarm for 1 more second. As I mentioned, it's a terrible idea to do any sort of printing in your interrupt service routine context, but we're going to do it anyway just to demonstrate something can happen here. Feel free to toggle an LED or set a global flag so that you actually print in your main thread. But to keep the code small, I'm going to go ahead and print and do the really bad thing. But note that that is a terrible idea to print from your ISR context. Like I said, that's just a demonstration. Now we're going to set up our main. We're going to have our return code that we are used to using, and we're going to set up our counter device here. This is the one that we will configure. We get the information from the device tree, in this case the myTimer alias. Remember that the dash gets automatically converted to an underscore so that it can work in C as a macro symbol. And we are going to get that alias, get the configuration from that, and that's what's going to be passed to our callback and what we're going to use to configure our counter. As you can probably expect, we've used this device struct a number of times in the past. It's a very common struct and way of working with stuff from the device tree that maps to an actual peripheral on your microcontroller, or something like an external sensor. By this point, hopefully you've seen it enough that anytime we use a device, we can rely on the driver code to initialize in the background during the kernel initialization sequence before this main entry point is called, which means it's a good idea to just do this device is ready check to make sure the device has been configured. So anytime you set up a device, make sure you call this is ready function. Let's scroll up so you can see what's going on. Next, we're going to configure the alarm, which is just setting some fields in a struct. In this case, we're using this counter alarm configuration struct. We'll set the callback to the counter ISR, that's the function we defined earlier. The ticks, we're going to use that same function, counter US or microseconds, 2 ticks, pass it in the device, as well as the number of microseconds we want to delay by, 1 million in this case, or 1 second. That will figure out automatically how many ticks of the counter need to happen in order to make that alarm go off. This is the interesting one. For user data, we're going to assign it the address of itself, of the struct that we're defining right here, so that when the callback is called, the user data points to this struct so that we can update the ticks. Flags are 0. We're not going to do any sort of funky flags here. If we want to take a look at what's going on here, so let's copy this. IntelliSense is not taking me there right now, but we can go to our API. We can look up this struct. Let's see where it's defined. Here it is. Here's the struct. You can see the alarm flag. So counter alarm flags. Here are your options if you want to change how this alarm works. All right, let's go back to code. Then we're going to actually start the counter. This is simply counter start. That's the function in the counter API that we call. We pass it in that counter dev, that device struct that we've created that's been configured from the device tree and hopefully initialized in the background for us. Once we get that return value, we'll check to make sure everything works okay. If not, we'll print that error to the screen and kill this whole program. Finally, we'll set the actual alarm to go off based on the alarm configuration struct that we defined earlier. We will call this counter set alarm function. We pass it in the device that we've been working with, the alarm channel ID, which is 0, we defined that earlier, and the configuration. Once again, if the return value is less than 0, we just print an error to the screen and stop. Just for fun, we're going to print the number of ticks to the screen so you can see how that conversion happened automatically for us. As we did earlier, we are going to do nothing in our main thread. We're just going to tell the thread to sleep forever. Let's go to the API reference. I want to point something out here. The struct reference, I want to go back to this counter interface. If we go look at this, you can see how this function is defined here. We have a channel ID, which means we could, in theory, set up multiple channels to have different alarms going off using the same hardware counter, which is really nice. That just means in your code, whenever your ISR is fired, you'd have to check to make sure your channel ID matches for that alarm you want to handle. So you can see when this ISR is called, you have the channel ID. I'm keeping this simple for now, but it would be a good idea to check to make sure that the channel ID matches the alarm that's going off, in this case, alarm channel ID 0, that you want to handle, and you could have multiple of those in your single ISR. With that, we need to create our CMake lists. I'm just going to borrow this from timer to save us a little bit of time. So I'm going to copy, I'm going to drop it in here. I'm going to change this to counter interrupt, the project name. Not that it matters, this is pretty arbitrary. And I'm going to make our prj.conf file. Let's leave that blank. Close out these. And let's bring up our terminal. Let's make this terminal a little bit bigger so you can see what's going on. We'll go into our counter demo folder. We're going to build this project, set our board, and note that this time we need to pass in the overlay file because we have modified the device tree. So let's let that run. And I've got an error in main. Let's go take a look at this. I just misspelled it. That dot needs to be an underscore. All right, let's try to rebuild. And we have this very cryptic error. Undefined reference to device DTS ORD. That's the ordinal number we saw when we were creating our own device driver, but this does not tell us where to look. The only hint that I have by looking at this is that this occurred during a linking stage. So we can see here LD is usually the linker, and that's it. Because this is a linker problem, this makes me think that this is a software issue, which is probably a kconfig thing. But man, this message is very cryptic because this DTS tells me it's a device tree problem. But the linker says this is a software problem. Whew, this is fun. When you run into something like this and you think it's a software issue, what I might recommend doing is looking through your Zephyr code, going to find where the actual source code is for the things you're working with. In this case, it's like the counter set channel alarm. We can go into Zephyr, we can go into drivers, and we know this is a counter. So if you search around, let's see. If we know that this is a driver, we can copy that, or maybe in the include, you can find where that's done. Yeah, this is all the C files. So let's search for that. Find in folder, search for that. Oh boy. Where's your actual definition for this stuff? Here we go, counter.h. And here's where it's actually defined. Okay, so it is in drivers. It's looking at counter.h. So if we go to our drivers, here's counter.h. There's no C file for this, so we're in include Zephyr drivers. This should match up with drivers where this is the source code that matches with those header files. And we can look through here to find something like counter. Here's the source code for all the counters. What I recommend doing is coming down, looking for your kconfigs, and there should be a top level thing just called kconfig. And here is it defining this menu config item, this symbol called counter. All of these things get enabled with if counter. So if counter is enabled, then all of these become available in menu config. You're welcome to play around with these, but we just need to figure out how to turn on the counter. It's probably that symbol. And a lot of times we have this CMake lists. It uses these Zephyr if defs. Come to the CMake lists. This is enabling the various counters. So counter has that top level counter here. That's a symbol we probably need to enable. ESP32 timer, and we probably need to enable counter timer ESP32, but it defaults to, yeah, so it defaults to on. So we don't need to mess with that in our own conf. If you're working with a different architecture, like, I don't know, the RPi Pico, if this said default N, you'd probably have to enable that symbol as well. So based on what we're seeing here, I think we just need to enable the counter symbol, which should control all of the counters, which means that's not specific to our architecture. That means we can put it in our prj.conf. So config counter equals Y. You could also explore this by going through the menu config options to find some of those symbols and see what you need to turn on. This can be a little complex and confusing sometimes, but let's save that and let's try to rebuild our project and see what happens. And it looks like it built. So that's all we needed to do was add this config counter up here to enable that software section for handling counters for us. But yes, those error messages can be very confusing when you get them. With that, let's stop our original timer. we are going to flash our demo counter interrupt this time instead of the timer. We'll go into build Zephyr, zephyr.bin, wait a moment while that flashes. When it's done, let's open up our serial terminal. And you can see that the alarm was set to 20,000 ticks, which makes sense for the APB clock and the prescaler we sent. And then every second, this counter ISR goes off and prints something to the console. Let's stop that. The last one we want to look at is pin change. These are kind of the most common interrupts you will likely use. There are others, but hopefully this demonstrates how you can set up your own interrupts, where to go for that information. But I find that I most often use timer interrupts and pin change interrupts when writing microcontroller code or firmware. So let's talk about how to set up a GPIO or pin level change interrupt. Let's close this down. We're not going to go back to our code, but for a moment, we're going to go to this API because we're going to look at this GPIO driver documentation. What we're looking for is this GPIO pin interrupt configure function that Zephyr comes with. Specifically, we're looking for the one that comes from a device tree rather than first having to get the device tree information and then pass it in. We can just use this _DT suffix function where we can just pass in a device tree spec and it handles it for us. It's basically just a wrapper for this function right here where it unrolls all this information from that struct. This abstracts away the setup for configuring a GPIO interrupt. This means we can once again create cross-platform code without having to worry about staring at the datasheet to figure out how to set up the correct registers for the different interrupts. We do need to set a flag here for the type of interrupt we want to use. So with this, we can go into the gpio.h file reference. We can also find this in the code as well if we want to, but we are looking for these GPIO flags T. And in fact, we could probably just click on that here and it takes us there. Yeah, there we go. This isn't a struct, rather it's a uint32t that holds the flags for us. And it's likely one flag per bit. But if we go to this file, this takes us to that file we were just looking at. If you scroll down, you can find the different flags. This is for the input-output configuration that we've seen before for configuring the GPIO as input or output. Keep going, you can find the interrupt configuration flags. This allows us to do things like disable the interrupt fires on a rising edge, interrupt fires on a falling edge, interrupt fires on any toggle, high to low, or on low, on high. If you've worked with microcontrollers before, you should be familiar with these types of interrupts when you're talking about pin levels. The one we care about is this GPIO int edge to active. Note that's not the same as a rising or falling edge because these will be determined by the actual pin level, whereas active we've set up so we could have a button be active low or active high, knowing that pushing a button means going active. So now we can have something that's abstracted away from the actual pin level and say edge to active, so that whenever a button is pushed, whether that's active low or active high, this gets fired. This helps us once again with abstracted or portable code. Let's go back to our code. Let's close down the previous demo. Let's get rid of the terminal. I am going to be particularly lazy here. So in episode 4, we had our demo button. We're going to copy this and just modify it to use an interrupt instead of polling. So I'm going to copy this. I'm going to paste it in my apps. I'm going to rename this to 09 demo GPIO interrupt. In here, we have our board overlay. This is already configured with the button information that we set up in a previous episode. Feel free to go back to the episode if you want to figure out how this is set up, but there are a couple of things we need to do here. First, we're going to get rid of polling mode. We are going to be using interrupts instead of polling. I misspoke a little bit in episode 4. I have since talked to one of the Zephyr developers who clued me in on what's happening here. If you were just using GPIO by itself in your code, which we did in that episode, this doesn't do a whole lot. This property for these buttons don't mean anything. What they are used for is if you go into Zephyr and you see this subsystem folder, these are a number of libraries that you can think of acting as independently from our driver code that we've been mostly using. This contains things like file systems, disks, some networking, a full console, Bluetooth. It's stacks and libraries that are pure software, usually that exist separately than our driver code. Normally we've been just working with driver code and we haven't dived into any of these subsystem libraries. In here, there is something called input. If you use this input library, which you need to enable with this menu config option called input, and then you can start using the API calling this library uses this debounce interval millisecond property from the device tree. So that's where it's used. We're not using the input library in that episode, which is why that property was not particularly used. Once again, we're not going to use that library. We're not using that subsystem, and we're just going to get rid of this property. Leave it at its default, whatever it was set up by Espressif. I think it was 30 milliseconds. It's fine. We're not going to use it. We are going to keep using GPIO pin 5, and we're going to set it as active low because that button toggles to low whenever it's pressed. That means pressing the button sets the pin to ground, which then in software means it's now considered active. So active low. We are going to use an internal pull-up so we don't have to have an external pull-up on that pin. This is a completely configured button. With the button connected in hardware on our breadboard, we are ready to go. So let's save that. In CMake lists, I'm going to make one change here. I'm just going to call the project something else. Not that it matters. PRJ, we don't need anything. We're not using counters or anything that we have to enable here. In source, we're going to make a few changes. We're going to keep these includes. We don't need this sleep time any longer. We're still going to get this GPIO information from the device tree, from this alias that we named myButton. We're going to assign that to this struct, this GPIO DT spec struct, and we're going to use that in our code. Then we're going to define our GPIO callback. Once again, this is executing in the interrupt service routine context, so we're outside of our main thread when this occurs. If you go back to our Zephyr docs, this GPIO.h reference, you can find the callback function. If you scroll through here, there's the type defs. Here's the callback handler. You can find the signature for our callback here. We need to pass it in the device that we've set up, a pointer to the callback, as well as the pins where the interrupt occurred. So that's why we have this signature here. To figure out which pin caused this interrupt, it's a good idea to look at the pins variable that was passed in and figure out which bit of that was set. In this case, we are going to take our struct, the btn GPIO DT struct. We're going to get the pin field from that and bitwise and with our pins. If that pin or that particular bit is set, then we know that it's the pin we're looking for in this button struct that we will configure. So you could have multiple button structs that wrap up the handling of the GPIO for you, and you could use this bit, which just left shifts a 1 by the number that's given by this pin, and then you would mask it here, so you could actually handle multiple pin presses in a single ISR with a similar masking operation. Then we're going to print to the screen, which in an ISR context is a bad idea, but just to show you that something can happen here, if you set a flag, want to handle something, we're going to print it to the screen and write out which pin was pressed. We're no longer going to handle stuff in main, so let's get rid of our state. We are going to make sure that the button was initialized correctly, just like we did before. We're going to set the button as input. The one thing I forgot to add here was some sort of message. Let's get rid of printing the flags. We've already demonstrated that. Then we're going to call this GPIO pin interrupt configure. That's the function that we looked at earlier in the documentation. We're going to pass it that button device that we get from the device tree. That goes into the function, as well as that flag, the int edge to active flag that we saw earlier. Rather than rising edge or falling edge, we want to active so that this is more portable code, as we know that pressing the button means active. Finally, we call these two functions to connect the ISR, that interrupt service routine, to the particular interrupt source. The first is this initialize callback function. Notice this is unique to the GPIO driver in Zephyr. So it's initializing the callback. We pass it in the callback data, the button ISR, that's a pointer to the function, and the particular pin. In this case, it's the bit for that pin, so we've got to call that bit macro to left shift that 1. We're also going to add the GPIO callback to essentially a callback stack that the GPIO system knows about. We give it the port from the button, as well as that callback data. And I believe I forgot to define or declare that callback struct. I'm just going to declare it as global. You could probably put it in main if you want to, or a static, so it's just to this file. So that means the initialization function takes in the ISR function, the pin or the bit. You could bitwise or the different bits for the different pins you want to handle. And that adds the one callback into this callback structure. And then we add the callback as part of the structure, as well as passing in the port. I'm assuming it needs to monitor the port here. So if we copy that function, if we go look at the information in the documentation, pointer to the device structure or the driver instance. So in this case, it's probably GPIO 0, GPIO 1 for the ESP32, which I have not verified, but makes me think that if you are doing pins on the GPIO 0, you'd need a different callback than if you were doing pins on GPIO 1 because they're two different controllers, and probably have two separate interrupt lines or buses for those particular controllers. I have not verified that, but that's what this makes me think. If you know any differently, please leave a comment. With that in mind, we have our interrupts set up, which means we can get rid of all this. We don't have to pull that anymore. We're just gonna put this thread to sleep. We're gonna say do nothing. Let's save that. By default in Zephyr, GPIO pins are set up to trigger interrupts, so we don't need to configure anything in the device tree other than setting up which pin we want to use. That's why polling mode was its own flag that's actually disabled by default. So we don't want to use that. We want to leave it like this. Zephyr assumes you're going to be using interrupt for your pin changes, which is why we don't have to do anything extra here. At least that's my experience with the ESP32. I'm assuming that's the case for most microcontrollers. With that in mind, let's bring up our terminal. I keep starting new terminals, but the reality is I can go back to one of these previous ones. Let's go out of this. Let's go to 09 demo GPIO interrupt. Let's build, and we do need to pass in that device overlay, which is DTC overlay file. All right, let's see if that builds for us. With that done, let's flash it. 09 demo GPIO interrupt build Zephyr zephyr.bin. Wait a moment while that flashes, and open up a serial terminal. We can press the button connected to pin 5 to trigger the interrupt. Whenever we press the button, you can see that the text comes up with button pressed and the pin number that is causing that interrupt to fire. Let's take a look at our code again. If we remove our terminal, go back to main.c. I probably mentioned this a few times by now, but doing a print statement in an ISR is a terrible idea. This is really bad practice. This can take a while, and often it's too long for an ISR, which blocks other things from executing. A common practice in embedded system programming is to set something like a global variable or a static variable up here that you then look for in your main thread. Whenever you see that set, you execute the thing that you want to accomplish. You can do that in Zephyr, there's nothing stopping you. But there's another cool feature you might want to consider. If we look in Zephyr through the documentation, you might come across this thing called a work queue. This is a default thread that's created for us, and it sits in the waiting state for something to show up in the queue. You add functions or function pointers to a queue that then go to this thread, and then the thread executes those functions in order. If you look through the configuration options, you can see where you can set up the stack size, the priority, no yield, but priority, which is really interesting, defaults to -1. There's some ways that you can disable preemptive or cooperative and set them, but by default these are enabled, so this goes to -1, which if you remember from the multi-threading episode, this is the lowest priority cooperative thread. So your function needs to return when it's done in order to give up execution to your other threads. So if we look at that, we can look at the thread priorities. You can see a nice little diagram. -1 is where this work queue thread operates by default. So you have your preemptible threads over here, you have your cooperative threads over here, and it's the lowest priority cooperative thread. You can find the work queue API. The basic usage is to create a work struct. You then call kwork_init to assign a function to your work struct, and then you call kwork_submit to submit work items to the queue. Your function that you submit to this will be called as soon as the work queue thread runs. There is no need to set up a separate thread or work queue. Zephyr enables one by default. It's known as the system work queue. If you want to set up your own work queue that's different from the default system one, you can do things like work queue init, work queue start. But for this challenge, you won't need to do either of those. Just rely on the one that's already set up by default. In fact, your specific challenge is to take this demo that we just made and modify it so that instead of having a print K in an ISR, which is usually very bad practice in embedded programming, add an item to the work queue and create a handler that's a function that just prints to the console. So just create another function over here, move this print K to that function, and in here, wherever you would handle it, add that function to your work queue so that it gets handled whenever the work queue thread runs. Even better, you can call this kwork_reschedule to add a work item, in this case your function, to the queue after a particular delay. So what I might recommend is making this delay something like 30 to 50 milliseconds. Then in your work handler, wherever you write that function here, check the button state to make sure it's still pressed. If that button is still pressed, write a fun message to the console, like just move this down there. This is a slick way of adding debounce logic while keeping your ISR fast and simple. I recommend checking out Goliath's Intro to Work Queues blog to learn more. This is a really good guide to understanding how to work with work queues. I hope this helps you get started using interrupts in your next Zephyr project. Next time, we'll tackle creating simple graphics using the LVGL library and an LCD driver. Stay tuned.